Hi all! This episode of Physical Attraction is brought to you by the American National Standards Institute. Standards make the world go round, and they also dictate what is round. Without standardised measurements and definitions, physicists would be speaking to each other in different languages and would struggle to understand the universe even more than we already do. You can learn about standards in America at the ANSI blog at blog.ansi.org/pod to learn about how standards apply to you. Now on with the show.
Into his eyes. They're the eyes of a man.
Hello, and welcome to this episode of Physical Attraction, the show that tries to explain physics, one chat-up line at a time. Today we're going to be dealing with the life and works of Isaac Newton, who cast a very long shadow over physics, and whose laws are still pretty much the first thing any physicist will learn when they start out. So for our chat-up line, are you breaking Newton's universal law of gravitation? Because you're unusually attractive. At which point, you probably have to backpedal rapidly and say that you're not accusing the other person of being unusually massive. Then you go cry in a corner and remind yourself that Newton was probably asexual and it helped him get a lot of stuff done. Because while it is true that Newton's law of universal gravitation means that everything with mass attracts everything else with mass, which means that you, listening to this, are undeniably physically attracted to me, and there's nothing you can do about it. Meow. Gravity is a very weak force by comparison to the other three. If you're sitting across the room from me, the attraction that we exert on each other is around 3/billionths of a Newton. That's tiny. Even if we're only a couple of meters apart, the force is the equivalent of the weight of about a grain of sand. So you're not exactly likely to come flying towards me in paroxysms of lust anytime soon. At least not due to gravity. And let's face it, not at all. And it also depends on how massive the objects in question are, and how far apart they are. So you're more attracted to all of the people who are closer to you, or all of the people who are at the same distance as me, but who weigh more than I do in proportion to the square of those distances. Which doesn't mean that we can't make it work, but by this measure, at least, the Earth will always love you more than I do. Back to Newton then, who loved science. When talking about famous physicists, any famous figure from history, you inevitably find that people tend to split into pro and anti-camps. This is because we like to paint historical pictures that are very simplified, and then we like to make ourselves feel clever by tearing them down again. So for every person who achieves the incredible heights of renown that Newton did, there are people who will attack their legacy for all sorts of reasons. Chances are a lot of the criticisms are valid, and with science historically often being discovered and lost, it's foolish to say things like Isaac Newton is solely responsible for modern physics and so on. The same is true for every fact I tell you about his personal life. But it seems clear that Newton, alongside Einstein, are two of the physicists in the modern era who arguably had some of the greatest impacts on the science. There is a reason why the history of physics is divided into before and after Newton lived. Same with Einstein. Whatever you think about the man, his was undoubtedly a rare genius. So he's an important enough individual that I think it's worth covering him as a person as well as the science that's associated with him. And I also wanted to cover him in a biographical way because by all accounts Newton was pretty eccentric. For example, he was a member of the Houses of Parliament for a few years. You'd think that such a renowned genius would have had a lot to say on the issues of the day, and might even be able to direct society towards enlightenment. I'm sure there'd be some popular support, although certainly not universal, for putting someone like Stephen Hawking in a position of influence today, compared to some other politicians. And he was representing the University of Cambridge too. You'd think that they might have something to say. But Newton was instead famously taciturn. Apparently the only time he ever is recorded as speaking, he was complaining that the chamber was cold and asking to close a window. He displayed some incredible snark, and the often outright anger towards people he disliked, especially his longtime rival Robert Hooke. If you're in Britain, or you've been to Britain, you might have a £2 coin. Look around the edge, and it says, "Standing on the shoulders of giants," a famous Isaac Newton quote that he said to Hooke about his work. Something along the lines of, "I very much enjoyed reading your paper. If I have seen further, it is by standing on the shoulders of giants." Famous quote. Oasis even named a rubbish album after it. By the way, I feel like after the world ends, the NME will still be publishing articles about the Gallagher brothers' ongoing feud. No one cares. But many people now think that he was mocking Hooke, who had kyphosis, what used to be called a hunchback. And alongside this, his temper is notorious. He frequently flew off the handle later in life, but even aged 19, the young Isaac, who listed his sins in an act of penance, for he was devoutly religious, mentioned amongst them, quote, "threatening my father and Mother Smith to burn them and the house over them." End quote. Burning down the house? Evidence of a troubled childhood? Possibly. Isaac's father died before he was born, and his mother remarried. That's why he refers to Smith, the name of Newton's stepfather. But then again, who didn't threaten to burn down their family home at least once while they were a teenager? It's a difficult time. So I can't resist a little digression into the matter of Isaac Newton's faith. He was a devout Christian throughout his life, but he was also what you might technically call a heretic. There's a bit of an overlap here with the Roman Empire, which anyone who's met me will tell you is a slight obsession, for which you can thank legendary podcaster Mike Duncan of the History of Rome. Anyway, when Constantine converted the Roman Empire to Christianity, he found himself a little bit frustrated with his chosen religion. Only 300 years after Jesus had lived, the church was already quibbling over little bits of doctrine, the interpretation of certain words, and so on. One of the key points in the argument for the early church was in the nature of the Trinity. And in the Eastern Roman Empire, whole civil wars would end up being fought partly on this topic. So Orthodox belief holds that the Trinity means that God the Father, God the Son, and God the Holy Spirit are all aspects of the same being, the same entity, but in Newton's opinion, whenever God was used in the Bible, it refers unambiguously to God the Father, and that therefore Jesus and the Holy Spirit are separate entities. So these various controversies were all being thrashed out in the 4th century by bishops Arius and Anathosius, with Anathosius and his view of the Trinity eventually winning out and becoming orthodox. This might sound to those of you who aren't theologically minded to be a tiny distinction, but it was enough to get you burned at the stake throughout many eras of history. Also, when the Mongol hordes were invading Europe, the Pope spent a great deal of his letter to the Mongol Khan explaining this correct view of the Trinity, concerned that he might be a heretic. The Mongol Khan obviously wasn't that interested. He argued that the only god the Pope needed to worry about was the one that was allowing the Mongols to win victory after victory. But the rest of this will be for my history podcast, which will launch at some point in the future. I think that the key point here is that Newton was, in many ways, a radical. When he was first being introduced to the Greek philosophers that had been taught in Cambridge for hundreds of years, he kept a journal of his thoughts. It was headed with a Latin inscription: "Plato is my friend, Aristotle is my friend, but my best friend is the truth." His willingness to question the orthodoxy of the Catholic Church was all a part of this truth-seeking. A healthy scepticism of accepted beliefs is absolutely a necessary component of science, I think. Intuition is your friend, so is belief, so is logic, but your best friend, your greatest friend, must always be the truth, followed closely by your ability to prove it. Like many young geniuses, Isaac Newton was misunderstood at school at first. His mother briefly pulled him out of education to run the household farm after his stepfather died. But this didn't work out due to a combination of Newton being ridiculously unsuited for running the farm, and his uncle's intervention eventually persuading his mother that he should go to university. To prepare for this, he lodged with the headmaster of the school in Grantham for a year or so, and by 1661 he was at Cambridge. Newton originally wanted to pursue a degree in law, but eventually his studies became far more mathematical. Mathematics was advancing, but physics, or natural philosophy as it was called then, was taught largely the same as it had been during Aristotle's day. Aristotle lived in the 4th century BC, so the fact that he was the foundational text for much of what was taught tells you something about how much development there had been in the meantime. One of the most difficult questions I've ever been asked is, what is physics? It sounds silly, but it's actually quite difficult to separate it from the other aspects of science, chemistry and biology in some ways. You might say that physics is the study of matter, light, energy, and how they interact. And that all sounds very, formal and proper and so forth, but then you get into questions. Chemistry is about energy, isn't it? And it's also about matter. And biology is about matter, it's just about living matter, and that has energy, forms of energy that we find. And so you see, it's a little bit tricky to really delineate where physics begins and other subjects end. And in Newton's day, there was no such thing as a subject of physics. There were certain people who looked into things like optics, there were people who looked into things like how bodies move, and there were people who were astronomers and so on. And there were precursors to all of the fields that would later become physics, but there was no such thing as physics back then. So, mostly, it was based on this natural philosophy of Aristotle, and as we know, he was a philosopher as well as what you might call a scientist, but he didn't really believe in the scientific method. It was more coming up with a theory and finding it to be vaguely in agreement with nature so that it seems like it's logically consistent, but not testing it through experiment. And that was in the 4th century BC. Now it's 1661, 2,000 years has passed, and he's still the standard text. Can you imagine anything like that happening today? But there are 4 major developments that we should talk about, all of which had an influence on Isaac Newton at some point or another. Copernicus was amongst the first of the Westerners to suggest that the Earth went round the Sun, what's called the heliocentric model. Incidentally, a bit of linguistics. Heliocentric, the Sun, Helios, at the centre. Helium is called helium because the element was first discovered by analysing light from the Sun. It wasn't discovered on Earth until much later. It's actually crazy that we put helium into balloons given how rare it is, a huge waste when it's also useful in MRI scanners and industrially. Luckily they found a big reserve of it recently, so we'll have abundant helium for a while yet. Just don't inhale it all to give yourself a squeaky voice. So Copernicus, who owed something of a debt to the Islamic astronomers before him who'd figured out that the Earth was moving and not stationary at the centre of the universe, suggests that we're orbiting around the Sun. Then astronomer Tycho Brahe makes some very accurate observations of the motions of the planets and so on. Kepler looks at his data and comes up with some key laws that apply to the motion of the planets. So what Kepler did was he looked at the experimental laws and then came up with something that you'd call an empirical law. That is to say, he figured out patterns that were obeyed by the data. He didn't necessarily know why they were obeyed by the data, but he knew they were obeyed, and because they come from empirical evidence, that is the evidence of our senses, we call them empirical laws. So Kepler's laws are essentially the following. All planets move in elliptical orbits with the Sun at one focus. Ellipses are squashed circles, and you can imagine that this means that one direction of the ellipse is longer than the other. That's the major axis. The focal points of the ellipse are 2 symmetrical points in the middle of the ellipse that help you define the curve. It's not quite the same thing as the centre, although it can give you a rough idea. That's law number 1, elliptical orbits with the Sun at one focus. Law number 2 is that if you draw an imaginary line that connects the planet and the Sun, it will sweep out an equal area in an equal amount of time. So you can see that this isn't necessarily intuitive that this would happen straight away, right? Because if the planet is a long way away from the Sun, then the length of the area that's being swept out is very long. But actually what happens is the planet travels slower so that it covers a smaller width in an equal amount of time. And it turns out that it does this in such a way that the area is always the same. So when the planet is really, really close to the Sun, and therefore the length of that area is much smaller, it moves fast enough to compensate. Law number 3 relates the time period of the orbit to the size of the orbit. Specifically, the square of the time it takes for one full orbit is proportional to the cube of the major axis. That's the longest length of the ellipse. It makes intuitive sense that bigger orbits might take longer, but this specific relationship is Kepler's third law. So why am I banging on about the laws? Well, Kepler's laws are observed relationships. Kepler noticed in the data that these things always turned out to be true, but he couldn't really explain them. When Newton discovers his laws of motion, he can use them to explain Kepler's laws. And this is an example of a key idea in what would become physics. Your theory is correct if it can explain the observations. Or sometimes you set up an experiment to make observations that will confirm or deny your theory. That's why Newton's laws of mechanics were such a triumph and his law of gravitation was such a triumph, because it explained what we already knew about the motions of the planets. Incidentally, I think it's kind of fun to think about how philosophically superstition actually led to all of this being possible. because men like Kepler and Bray were astronomers, but they were also astrologers. Astronomy is the science of space, while astrology is the superstition of space, star signs, that kind of thing. I was always especially sceptical of star signs because I have a twin brother, so since he was born on the same day, surely no one could have a closer star sign to mine than him, and yet we have very different personalities. Kepler was probably also sceptical of astrology, but that was his actual job. He was employed by the Emperor Rudolf II, principally to read his horoscope. Without astrology, it's likely that funding for telescopes would have been a lot harder to come by. So if you're listening and you're an academic trying to get funding in your field, convince the politicians, our modern versions of kings, that you can use it to tell the future. It never fails. So before Newton, there was Kepler and Copernicus. And there was also Galileo, who made massive improvements in various fields. He contributed to mathematics. He was one of the first people who realised that the laws of nature were best expressed mathematically. He built better telescopes than had been constructed for a very long time. And he used something called parallax, the apparent motion of stars as the Earth moves, to learn more about the heavens. He discovered the moons of Jupiter. He observed the stars, and he even tried to measure the speed of light before people even knew that light had a speed for sure. Unfortunately, the methods he was using were nowhere near advanced enough to detect the speed of light, and so he concluded that it must be infinite, because it was just too fast for him to see. Galileo is very famous for an experiment supposedly involving the Leaning Tower of Pisa, where he tested the theory that feathers will fall at the same rate of cannonballs. This experiment was probably done before Galileo, but there's evidence that Galileo did understand what would later be part of Newton's first law of motion. He said that in a frictionless world, an object given a finite speed would carry on going forever. This is an example of where your intuition and your observations of the world can lead you astray. Because if you think about day-to-day life, it's not frictionless at all. One of my chat-up lines is, let's you and I get together so that we can empirically determine our mutual coefficient of friction, which is just filthy when you think about it, so try not to. But based on your observations, the idea that if you give something a kick, it will carry on moving in a straight line forever, well, that's completely contrary to what we see. You can't blame Aristotle and the Greeks for thinking that things naturally slow down unless you push them, or that the natural way for things to move is arcing downwards. So if you throw a ball from your hands, you'll see it arc downwards. They thought that that was just the natural way that things moved, unless something acted on them. And we now know that it only moves that way because gravity is acting. And the natural way for that ball to move, if there were no gravity, would be to just carry on going in a straight line forever, until another force acted. So it makes sense to think that things naturally slow down, or that the natural way they move is to arc downwards, because our Earth is filled with friction and gravity. But if we were conducting all of our experiments in a more typical region of space, surrounded by the cosmos, drenched in nothing, we would see the laws of nature for what they are more easily. But based on a friction-filled planet Earth, our point of observation, it's not intuitive that these laws are true. And that's why this idea took so long to become accepted. The final thing to mention that was a major departure from Aristotle was that Islamic scholars had published some pretty important textbooks on optics, including most famously the Book of Optics by Ibn al-Haytham, which contains some very interesting and important ideas. Many people before him had thought that vision arose due to something emerging from the eyes, rather than light entering the eyes. Alongside this, important experiments about refraction, reflection, and transmission of light were conducted by Islamic scholars 600 plus years before Newton. One of the key points here is that Ibn al-Haytham was one of the early advocates of coming up with ideas, or hypotheses, and then testing them by experiment. This is the scientific method. You come up with an idea, and you see if it matches the real world. You see if it can explain experiments or observations in the real world. That's the scientific method. It's this idea, applied to various different fields, that is essentially the most important aspect of what changed in the 17th century, around the time of Newton, and started this rapid acceleration towards the world we live in today. It's this idea, more than many other things, that have meant that in the 17th century, the world was indistinguishable for in terms of how you lived your day-to-day life from 200, 300, 400, 500, 1,000 years ago. But today, 100 years is an unimaginable amount of time in terms of how you can live your life. It's this rapid acceleration that was kicked off by the scientific method. So Newton was an advocate of this. Galileo was also a big proponent of this, but Ibn al-Haytham got there first. Notching up their improbable second mention in this physics podcast about Newton, the Mongol horde are kind of partially responsible for a lot of this science being lost when they destroyed vast swaths of the Islamic civilizations that had arisen before in the 13th century. So we can see that Newton was indeed a rare genius, but as is so often the case with really revolutionary change, the groundwork is laid by the seemingly slow period beforehand. The developments that Newton and others made laid the groundwork for the Industrial Revolution. The Russian Revolution in 1917 is another example from history. On the surface, it's incredibly dramatic. A monarchy, a far-right monarchy, is toppled and replaced by a communist government, a swing from a far-right autocracy to the far left. But the groundwork had been laid for hundreds of years in Russia, both intellectually and in terms of revolutionary movements that had been going for centuries, and hundreds of years before that time, it had been laid in the French Revolution and the English Civil War. Newton read a great deal of the old Greek-style mathematics of Aristotle, Plato, but also some of the newer, more scientifically minded ideas of Descartes, Boyle, Galileo and Kepler were starting to draw his eye. He quickly realised that to understand astronomy and astrology, he would need to learn mathematics, so that was the next step. It was in mathematics that his first real developments would start to come. In 1665, he received his degree from Cambridge, without too many mind-blowing discoveries along the way. His notes at the time have come down to us. Questions concerning natural philosophy. Alongside notes on the texts he was reading, we can see the beginnings of his scientific evolution. He accepted and liked the theory of atoms that the ancient Greeks had come up with under Democritus, but was out of fashion now. He was interested in light and colour, but he criticised Robert Hooke's idea that light was a wave. He ruthlessly criticised the theories he didn't like, coming up with counter-arguments and counter-evidence from his own life, even when the theories were by renowned scholars. He even questioned whether you could manipulate gravity to create a perpetual motion machine. By the way, no, you can't. Like many famous geniuses, you can hear rumours going around that Newton was a poor scholar, and it's true that while he was an undergraduate he didn't get the highest marks out there. But this is probably less down to the fact that he wasn't smart or dedicated to his studies, and more to do with the fact that his studies were mostly extracurricular, the new science of Kepler and Galileo, rather than the old science of Aristotle that they were actually testing him on at Cambridge at the time. In 1666, that portentous year with the 3 sixes, twin historical events struck Great Britain. The plague, which forced the University of Cambridge to be closed, and the Great Fire of London, which may have put an end to the plague. When Cambridge was closed, Newton was forced to return home to Lincolnshire for a couple of years, and it was there that his scientific career began in earnest. And it's here that we'll stop for this episode. Next time we'll get into the discoveries Newton made in his early career, the mathematics that would become calculus, his research into optics, and start to touch on his obsession with alchemy. And of course, if we have time, we'll get to that one time he had his brain smashed in by a rogue anti-science apple. Thanks for listening to this episode. There's so many things that you should be doing right now. You should go onto Facebook, and you should like the Physical Attraction Facebook page. You should follow us on Twitter. If you're not on Twitter, it's a really great way to waste most of your life. We're on Twitter at PhysicsPod, and also there you can see a PayPal link. So if you've enjoyed the show, you might want to throw $1 my way, a couple of dollars, $1,000, a couple of dollars is probably worthwhile. Everything you do helps us keep the show running. I pay hosting costs and spend an inordinate amount of my time writing this show and recording this show. So if you want to show a little appreciation that way, you can do it. But of course I know that not everyone can do that, and so one thing that it would be really lovely if you could do is just tell one other friend about it. You can like us, review us on iTunes, but if you just tell one person to listen to the show, and when you follow up in a week and say, "Did you listen to that show yet?" they might say no. And you should probably tell them again that, it's really good and you might enjoy it. And then a week later, if they still haven't listened to the show, then you should be a little bit firmer. And then if after another week goes by and they still haven't listened to the show, I'm not saying you should force them to. That would be wrong. I'm just saying that if every one of you listening tells one person about the show, in 30 episodes' time we'll have 1 trillion listeners. Can you imagine? That's the power of exponential growth. Until then, don't burn down any houses, and be kind to each other.